Good morning viewers. Welcome to this session. In this session, let us focus on process management in operating systems. I am Professor V.V. Subramaniam, Director, School of Computer and Information Sciences, IGNOU. So in the earlier session, we had seen what is an operating system, what are its goals, what is the purpose of an operating system, what it provides, what are the basic functions of operating system, and then types of operating system. So there are several basic functions for any operating system. Like it starts with the process management, memory management, device management, file management, security and protection, and error handling. So amongst these particular functions, let us start with the process management in operating system. So this particular unit pertains to MCS 041 operating systems, block 1, unit 2. So what exactly is a process and what is the basic difference between the process and a program? Let us start with the definition. The term process, whenever we use, is the program in execution. The term process was first introduced when they had used the Multics operating system. In order to define the process in execution, in the program in execution, they had coined a term called as process. So it happened in 1960s. So a program just residing in the hard disk, we can't call it as a process. So whenever it is in execution, that is in execution, then it can be called as a process. Program in execution is called as a process. So for example, a batch job can be a process, a time shared user program can be a process, a system task such as pooling is a process. Suppose if you have given the print command and the printing is happening attached with some program execution, then it can be called as a process. So let us see the basic difference. A program is a passive entity, but a process is an active entity. That is the basic difference. Just residing in the hard disk or secondary memory, we can't call it as a process. However, we can call it as a program or set of programs that they are residing in the secondary storage. But whenever they are residing in the RAM and executing, then we can call it as a process. It is known that two processes may be associated by using any fork or any threads. So whenever a program is being split into some processes, that also happens sometimes, that those may be parallelly running, some may be dependent, some may be independent. So then also we call them that a main process is being split into sub-processes. Then in multi-programming system, processes are performed in a pseudo-parallelism, as we are seeing. A program may be having a condition otherwise, and depending upon the condition, a function may be invoked, and that also can be called as a sub-process. Or else parallelly two processes, the main program may be initiating and those may be running parallelly. So these may be the cases wherein which in the parallel programming systems. In fact, there is only one processor, but it switches back and forth from the process to process. Here, suppose if a RAM, the main memory, is having P0 to P5 processes residing at the same time. So the CPU, the processor may be attached to P0 for this instance, and whenever there is a kind of IO interrupt or any error happen, then obviously depending upon the algorithm that is running behind, the CPU will be transferred to the other process. So likewise the switching also will happen. So whenever we talk about the process, it may consist of some IO burst part and some CPU burst part. What is CPU burst part? That is processor burst part. So that is nothing but the program which is attached to the processor and is executing, those instructions comes under the CPU burst part. And coming to the IO burst, this is nothing but it is interrupted for some IO device or else IO job to happen. So those kinds of bursts or those kinds of instructions which prompt something happen to the IO to happen, those are called as input output burst jobs. So a process will be having mix of both. Some instructions pertains to processor bursting and some instructions pertain to IO bursting. So here you can see the CPU bound process and the IO bound process, or else you can see in some processes both the things also can happen. So in the CPU bound process, it spends more time doing the computations and very few long CPU bursts. And then coming to the IO bound, it spends more time doing IO than the processor computations. So it depends. Some processors they will have equimix. Some processors the CPU bound will be very much high, that is processor burst will be very much high and IO will be very much low in that context. And in some processes you can see IO will be at higher, at peak, and there will be very little interaction with the CPU. So these particular things, depending upon the job, depending upon the process, it executes. Either it may be a CPU bound, either it may be IO bound, or else it may be a mixed kind of thing. So there are certain responsibilities whenever we talk about the process management. Here on the slide you can see there are several responsibilities mentioned. So all these responsibilities grouped together comes under the process management and should be handled by the operating systems. So the process creation, after the process is happened, the termination of the process, whenever the process is happening, suppose if some interrupts are happening meanwhile, those should be handled by the operating system. That means the controlling from one process and to another process in the same RAM. Then as per the algorithm running behind the scheduling, that also should be taken care. The dispatching, whom to get the next processor, interrupt handling, exceptional handling, switching between the process, that is the context switch, process synchronization, process communication, management of processes of PCBs. This particular thing we will learn in due course of time. So all these 9 to 10 responsibilities, those are listed over here, comes under the process management, and they should be handled by the operating system. So when we talk about these particular responsibilities, then system software pertaining to execute all these responsibilities will be there in the operating system. So we had listed, but internally whenever it should deal with such kind of responsibilities, some set of programs needs to be written in the OS to handle all these responsibilities. So the programs or as the system software which perform these kinds of responsibilities comes under the process management system software of an operating system. So let us see, when we talk about a process, we had seen a process of higher CPU bound, a process with higher IO bound, or else a process with mixed CPU and IO burst. Then there are variety of processes we can talk about. Altogether, we can define two kinds of processes. One is an independent process, or else second category comes in the form of cooperating processes. So independent process, as the name suggests, it is not dependent on anything, like it doesn't have any effect on the other processes. It independently initiated, attached to the CPU, then the process executes, then terminates. So it doesn't have any talk with any other process, it doesn't need to have any synchronization part. So it itself is an independent thing, comes, executes and go by itself. When you come to the cooperating processes, these cooperating processes are a bit complex. So in these cooperating processes, these can affect by another processes executing in the system. So some may be like an initial process will be there, the main process. Then inside the main process, there may be a time which is two parallel processes, sub-processes may be started. So once again, they are linked to the main program, as well as maybe those two processes may be having a kind of cooperation or a kind of communication in between. Sometimes the possibility of synchronization should also be happening. So with these two differentiations, we can move ahead. The independent process, their state is not shared in any way by any other process. They are not at all dependent on anything. They are independent and their execution is deterministic. The result of execution depend only on the input values that the user has provided. Their execution is reproducible. The results of execution will always be the same for the same input. There won't be any variation. If the same set of input is given 100 times, then also the output will be the same. And their particular execution, whenever they execute, there doesn't depend upon any other process. There doesn't have any communication with other processes which are residing in the RAM. Their execution can be stopped and restarted without any negative effect. So this is all about the characterization of a independent process. When you come to the cooperating processes, it is quite contrast. You can see their states are shared by other processes, and depending upon the process start, sometimes suppose the synchronization misses, the results may vary. Their execution is irreproducible. The results of execution are not always the same. Sometimes if the synchronization or something happens, goes wrong, the results may vary. If you test it for 3 to 4 times, the result may vary. So this you have to keep in your mind coming to the cooperative. So the synchronization part, the communication part should be well designed, well written in the program, so that when it becomes a process, actually whatever we intend or whatever we desire as the output, those particular outputs can be expected. So coming to the relationship between the processes. In the concurrent environment, basically processes have two relationships. Either they may compete or else they may cooperate. So this is not true for the single process environment, wherein which the process resides, only one process resides in the RAM. The process execution starts, CPU is attached, the process execution starts. Whenever there is an IO requirement, the PCB is stored and then it is pushed to the IO queue. Once it is happened, once again it comes and starts the execution where it had stopped earlier. So this is the way for the single process. When you come to the concurrent environment, then many processes residing in the RAM and the processor is attached to them in any type of execution of the algorithm going behind them. So that particular thing have two kinds of relationships. One is the competition and the other is the cooperation. Processes compete for the resources. So once one process requests for the resource that is being allotted, if it is free, then whenever P1 is attached to process resource 1, P2 may have a requirement of the same process, so then it should wait. It should wait for the process to get on. So in addition, a collection of related processes that collectively represent a single logical application cooperate to each other. So first of all, you go take it, your preemption, your priority is high, you take the resource, perform, and then after leaving that particular resource, another process will take the same resource and use the resource. So any process, when you talk about, it may be of any of the process states like new, ready, running, wait, or terminate. So any process, when it executes, it changes the state. From the new, that is, the process is being just created. So when you talk about the ready state, the process is waiting to be assigned to a processor. You have to correct it, processor. Then running, instructions are being executed. Suppose if it is in the wait state, that is nothing but it is waiting for an event to occur, or else it is waiting for a resource, or else it is waiting in a queue wherein which the resources are there. So terminate means the processes executed perfectly and finished the execution. So let us see the same process state with the help of a diagram. You can see the new state, then when they are admitted, just born, when they are admitted, they comes into the ready state, and then when the CPU is attached, they will go to the running state, and when there is an interrupt or when there is an IO request, once again it will go to the wait state, waits for the resource to be attached. Then once the resource is being completed, the event after the event completion, it once again go to the ready state, picked up for running. Then once the whole execution is over, it is being terminated. So you can see here all the states are depicted in the same figure. The new state, the ready state, running, then waiting, once again going to ready, once again running, and if the process is successfully completed, it will be terminated. So whenever we talk about this particular computing of the processes, obviously a new data structure comes into picture, that is the process table, or else you can call it as the process control block. This particular process control block can have three names. One is process control table, process table, process control block, or else you can call it as a switch frame. So this process PCB comes into picture when we implement the process. So when we implement the process model, the operating system maintains a data structure. So that particular data structure has, the operating system maintains a table, an array of structures called as the process control block. What is the job of a process control block? Each entry identifies a process with information such as process state, its counter, the number of files it has opened, what all the memory allocations that it has, the status, the state of the process, process ID, all these things are being stored in the form of a data structure, and that data structure is called as the process table or process control block. Why this process control block is required? When we talk about the context switch, that is switching from one process to the other process, earlier processes details should be noted down somewhere, because once it went for the interrupt handling or else IO request, then what it happens is the complete state of the process should be stored somewhere, the snapshot should be stored somewhere, so that whenever it comes back to the ready state and the processor is assigned, that snapshot is required. So where to start? What was the last instruction that was executed? Where the file lies? Where the data lies? What was the ID of the process? So all these things should be loaded once again, and then the processor will be executed by the processor. So for that reason, that's the storing of the snapshot, and once again when it returns back after the event handling is happened, so then the PCB is loaded and then the process will be continued further. So in another word, it must contain everything about the process. The complete status of the process needs to be stored somewhere. So that is called as a process control block. So let us see what all the PCB contains. First of all, the PCB contains the process state, which may be new, ready, running, wait or halted. So any of these 5 states will be stored in the PCB. The process number, you can call it as a process ID also. Each process, whenever it is running in the RAM or else the main memory, it will be identified with a process number or else a process ID. So that process ID will also be stored. Program counter will be stored, which indicates the address of the next instruction. So if at all some 5th instruction is been executed and there it required some IO to happen, so it stores the next instruction like the 6th instruction, because whenever it returns back, then it should start from the 6th instruction onwards. So that will be recorded in the PCB. CPU registers the memory management information, which includes the limits like the upper bound, the lower bound of the process, everything will be registered. The IO status will be registered. Processor scheduling information will be registered. But not the least, the list of opened files. So along with this particular process, suppose if 3 files, .dat files are being opened, that particular information also been stored in the PCB. So let us see in the form of a figure. You can see here the pointer, that is the address location, the process state, process ID, then the program counter, that is the next instruction that needs to be executed, complete registers, the values, then memory boundaries, list of files, those are opened. So all these particular items constitutes a process control block. So let us see the context switch. So we had studied about the process control block. Then whenever the context switch happens, then the PCB plays the major role. So this particular context switch is also known as process switch or else task switch. In some languages we use it as a task switch, like in Windows we call it as a task switch. For Unix system, Unix based systems like Multics, Unix, Linux, IRIX, so these systems we call this particular process as the process switch. A context switch is switching of the CPU from one process to another. It is suspending of one process on the CPU and another process is attached to the processor, and it will be then executed after. Suppose if it is a new one, everything will be loaded. Otherwise, if it is the old one waiting for the processor, then the PCB will be loaded, and then from the next instruction of that particular process will be executed. So here, whenever we talk about the context switch, the PCB has a greater role to play. So whenever the processor shifts from one process to the other process, suppose if P1 is there, P2 is there, P1 till now is CPU bound and it has an interrupt happened, some event happened, so it has to stay in the IO queue or else some interrupt handler should be executed. So it is been suspended. Whenever it is been suspended, the complete information is being stored as the in the form of a PCB data structure. So whenever it resumes for the second time, all this PCB information will be loaded, then it will be executed using the processor. Let us see here with the help of a figure. Process P0 we had identified at the extreme left, and then process P1 at the extreme right. So two processes are residing in the main memory. So P0 starts executing. So meanwhile there is a kind of event to be happened. So there is a kind of switch mechanism over there, wherein which it should get the interrupt routine to be executed. So there the P0 suspends its operation. The complete information is stored in PCB0. We are identifying with a subscript PCB0. Then the CPU will shift to P1, and afterwards the complete PCB1, suppose if it is running, it has been a resumed kind of operation, resumed kind of process, PCB1 information is loaded, so it has the complete information. From the next instruction where it has left over, from that instruction onwards, for the process 1 it will be executing. Suppose once again P1 got an interrupt or IO to be handled, then the CPU is suspended, the complete status is being stored in PCB1, then it will resumes with the P0 by loading the PCB0. Hope you got understood the context switch. Here it is switching from P0 to P1, once again from P1 to P0. This is how the context switch happens, or else this is how the task switch happens. So let us see the scheduling of processes. So it is not a simple thing, just as we orally saying P1 is called or P1 is scheduled, P2 is scheduled, P3 is scheduled from the ready queue. So this is not just like orally we are saying. So whenever we talk about the scheduling kind of aspect, it is the fundamental function of an operating system. So which process needs to be scheduled, which process needs to be terminated, how many processes can be scheduled at the same time, or else how many processes can be kept in the RAM at the same time, how the context switch happens, so when to give the process the control of CPU, all this comes into picture when we talk about the process scheduling. So here CPU is the basic primary resource we are talking about. Its scheduling is central to the operating system design. So whenever we are talking about the process, why the processes are staying in the main memory? For execution. So here the CPU, the RAM and the coordination between the processes, or else coordination between the processes and the processor, everything comes into picture. So the main focus we are seeing here is on the CPU. So the primary focus is on the CPU, allotment of CPU to the various processes lying in the RAM. So scheduling refers to a set of policies that is the principles, or else you can call them as the guidelines or mechanism supported by the operating system that controls the order in which the work to be done for various processes residing in the main memory. So the main objective of the scheduling is twofold. One is to increase the CPU utilization. That is the first objective that needs to be taken care when we talk about the processor scheduling. The second aspect that we throw focus is on the higher throughput, that is per unit of time. You can take it as per 10 minutes or for half an hour, whatever the unit time that you consider, how many jobs were completed, how many processes were successfully completed. So both these things have the equal kind of objectives to be done while thinking about the process scheduling algorithms. So when we talk about the process scheduling, then there are two types of schedulers available. So first of all, see what is the scheduler. It is a simple program or else a system software written in operating system that selects the next job in the ready queue to be admitted for the execution. So this is called as a scheduler. So the primary job of the scheduler is to schedule the processes from the ready queue in order to give the allotment to the CPU. So this scheduler has a different name. Some people they call it as a dispatcher. So long term dispatcher, short term dispatcher, they call this scheduler as the dispatcher also. The primary job is to select the next job in the ready queue to be admitted for the execution. So coming to the scheduling objectives. So when we talk about the processes scheduling, so there are certain objectives. The primary objective is what we had seen, the higher the CPU utilization, and then the throughput must be very high. So both these things are the major objectives whenever we go for the scheduling algorithms. Remaining objectives you can see over here, the maximizing the throughput, be predictable. So once the process, we talk about the process, the OS should predict its time also, like how much time it requires in order to complete the job. So some sort of predictivity should be handled, should be there. Minimize the overheads, balance resource use. So all the resources at a dispose should be done, should be having a kind of balance, where in which the deadlock should be avoided. That particular deadlock we will see it in the next session, but the deadlock should be avoided. All the resources should be balancedly given, allotted, and then suspended and given to the other processes which are lying in the queue. There should be a kind of balance. Otherwise what we can see is, suppose if one resource holds the one process holds the resource and it is never giving up, then there may be the queue wherein which it will be growing and the starvation may takes place. One process is holding the complete resource and the other processes are waiting for the resource to get released from process. So there may be a never ending waiting happening over there. So a kind of balance mechanism is required in order to handle the resources very efficiently. So achieve a balance between the response and utilization, avoid indefinite postponement. That is what we are telling. So once there is a kind of preemption, that is a process having the highest priority executing the job, and then when it got stopped or else when it got terminated, another job came with next higher priority, and the lower priority jobs are being just withheld just like that, and the postponement of the processor to those lower priority jobs is happening. So that should not happen. So indefinite postponement of executions for the lower priority jobs should not happen. So enforce the priorities. Sometimes they may be helpful whenever a short job comes and there is a big batch job going on, then it may be temporarily suspended in order to provide the CPU to the process with the highest priority, that too with the shortest job. So then there may be a kind of like a provision to be given to that priority job by suspending the batch job temporarily, and then both the things will be given the balanced priority, and this can be executed very fast and go, and the batch process can be resumed. Given preference to processes holding key resources. So once there are some processes may be holding the key resources, and those must be given the preference. Why? Because those particular key resources are the resources wherein which many of the processes requires. So keeping in mind of the requirement of that key resource to many availability of requirement of that key process to many of the processes staying in the RAM, the key resource handling should be done very effectively. So degrade gracefully under heavy loads. Suppose if the system is having heavy load, it should say somehow to stop allotting more processes in the RAM. So it should have a kind of scheduling mechanism wherein which in order to piling up the jobs in the RAM, it should say temporarily hold on, so that the heavy load job is being executed properly and then it is being terminated, and later on the chance will come to the next processes in the RAM. So that kind of graceful degradation should be happening whenever we talk about the scheduling objectives. So as we have seen types of schedulers, there are two types of schedulers. We had seen the definition of the scheduler. So there are two types of schedulers. One is the long-term scheduler. It selects processes from the process pool and loads selected processes into memory for execution. And then there is another type of scheduler called as the short-term scheduler. Short-term scheduler is nothing but this particular scheduler is called as the CPU scheduler. Why? Because whatever the processes that are brought into the main memory by the long-term scheduler, the short-term scheduler, depending upon the algorithm, assign the CPU. So assignment of CPU to the waiting jobs in the waiting processes in the RAM is the job of the short-term scheduler. Bringing them from the wait queue to the ready queue, or else bringing them, readying them and bringing them to be residing in the RAM is the job of the long-term scheduler. So it is called as the job scheduler. Or else for the short-term scheduler, assigning the CPU to the already residing processes is the job of the short-term scheduler. So this short-term scheduler is also called as the CPU scheduler. So long-term schedulers are very fast, very slow. Why? Because it is the job of the long-term scheduler to take the processes from the wait to be loaded into the main memory. So once the main memory is full, it should be waiting in order to make them ready and putting it once again into the RAM. So it should be waiting, and then it is an infrequent kind of thing, and it is slow in the sense that it may take place once in some seconds or minutes. So the long-term scheduler controls the degree of multiprogram. More the jobs it shifts to the RAM, executes them, the degree of the multiprogramming increases. When we talk about the short-term scheduler, it is very frequently happening because the context switch happens here, and then depending upon the context switch, the CPU is assigned to the processes in an order, and it has to be a very fast execution kind of thing. And then this particular short-term scheduler focuses on the processor utilization. Processor should not sit idle. Processor should handle the one process after the another process. There should not be any delay time. Once it is sitting idle, then the throughput or else the processor utilization will be degraded. So we are not using that particular processor 100%. So the main focus of the long-term scheduler is the degree of multiprogramming, and then the main job of the short-term scheduler is to see the better processor utilization. So there is one term floated called as the medium-term scheduler. So it can sometimes happens to be good to reduce the degree of multiprogramming by removing processes from the memory and storing them on the disk. This happens whenever we talk about the load, heavy loads. So there may be a kind of thing wherein which we no more need the processes to be kept in the RAM, the heavy load process is going on, and this particular medium term scheduler sometimes what it does is it will deload, or else it will take the jobs from the RAM and then it will store them back onto the disk. So this swapping, this process of loading them back onto the disk is called as the swapping out, or else taking back from the disk to the RAM is called as the swapping in. The whole process is called as the swapping, and then in is to getting them inside to the RAM, and out is throwing the processes from the RAM to the hard disk. So you can see here the job of the medium term scheduler. So ready queue is there, then CPU is attached to the process. Whenever there is a heavy load or something is there, then some of the processes are swapped out using the medium term scheduling algorithm, and then once again the RAM is free or else the CPU is about to become free, then the processor swapped in, put them in the ready queue, once again the CPU is attached to them. So here that is how the medium term scheduling is happening. So medium term scheduling is very much nearer to the swapping process, swapping in and swapping out process. So process scheduling queues are there. So the queues are maintained for the processes. Suppose if you take the case of a job queue. Job queue is nothing but all the processes, those are waiting for the system. Set of all processes in the system, that is the job queue, which are about to get the, which are about to load them into the CPU. So they are waiting in the job queue. Ready queue is the set of all processes residing in main memory, ready and waiting for the CPU to get them executed. So those are the ready queue. Job queue or the pool. So a queue will be maintained here in the form of job queue, or you can call them as the process pool of processes. So those are waiting to get them transferred to the RAM. So once they are transferred to the RAM, so that is the ready queue, and those processes are waiting for the CPU to get assigned to them. And there may be certain device queues also. Suppose if printer is attached, then there will be a queue in order to procure the printer and get the job done by various processors. Suppose if hard disk is there, that may be one of the resource, and then some external magnetic tape is attached, magnetic disk is attached, or else CD drive is attached, or else external hard disk attached. All this comes under the resources. So there may be a situation where in which the processes will be waiting for the resources. So though each and every device maintains a queue, and those are called as the device queues. The set of processes waiting for an IO device is called as a device queue. For various device queues, there may be various queues attached to the device itself. Then process migration between the various queues. So once it got done, the resource is being attached, the things happened successfully. Suppose for the printer, the printing job done for the process 1. So once again it should be transferred to the ready queue, and then from ready queue once again the CPU will be attached by loading the concerned PCB and executing the next instruction. Not the vertically kind of thing, you see the horizontally. First horizontal, that is ready queue. Here we had seen the ready queue. So in the ready queue you can see there are two kinds of locations, one is the head and the other is the tail. So the head location is being noted down, the address is being noted down in the head, and the last thing is noted down in the tail. Suppose if the processors are increased, suppose if now the PCB 1 comes, so from tail the link will be detached from there and PCB 1 will be attached, and then PCB 1's information will be stored in the, or PCB 1's address will be stored in the tail, and the number count will be increased to 3. So likewise the second figure is the magnetic tape queue, or else you can call it as the input queue, input device queue. There is no queue, none of the processes is waiting for the magnetic tape. So for that reason head and tail are grounded. So no need of writing any information. Suppose if some 3 processors came into the ready queue of the magnetic tape in the first come first serve basis, then the first address will be stored in the head and the third process address will be stored in the tail. So likewise the queue will be maintained. This is a simple data structure wherein which you had studied in MCS 21. Likewise you can see magnetic tape unit 1 and then disk. There are 3 processes waiting for the disk and their locations are stored, and then terminal unit also only one process is being waiting in the queue. So this is how the queues are being maintained in the with the help of the operating system for various IO devices. So this is the kind of representation of process scheduling what we are talking about. So in the ready queue, that is in the ready queue means they are staying in the RAM and waiting for the process to get assigned to them. So that is the ready queue, and once one process is been assigned the CPU, the process is executed. You can see there may be an instance of an IO request, or else the time slice expired in the round robin fashion, fork of a child may happen, or else wait for an interrupt may happen. So depending upon these particular interrupts or events, the queues will be maintained, or else the corresponding software may be executed, the routines may be executed, and once again after executing those particular routines, they are being pushed once again to the ready queue, and once again they will be waiting in the ready queue in order to get the CPU assigned to them. So this is a complete picture wherein which it shows the representation of the process scheduling. So there are several algorithms we can talk about in the scheduling system, processor scheduling system. The goal of the scheduling algorithm is to identify the process whose selection will result in the best possible system performance, whether to give in queue, or else whether to honor the priorities, or whether to assign the processor depending upon the events that are happening, whatever the case may be. The ultimate goal that needs to be looked into is the best possible system performance. A major division between these algorithms lies in preemption and non-preemption. Preemptive scheduling and non-preemptive scheduling. Let us see one by one what is preemptive scheduling and what is non-preemptive scheduling. In the non-preemptive scheduling, this is a kind of category wherein which if once the process is attached, has been allocated to the CPU cannot be taken away from the process until and unless there is an IO job to be handled, or there is a simple error routine to be handled, or a simple interrupt that has been occurred during the execution. Apart from that, once the CPU is allotted, till the process completion, it won't be disrupted. For this non-preemptive, there are several examples which can be listed. The first come, first serve, that is the queuing system. Those can be considered as the non-preemptive scheduling algorithm. Shortest job first, that also comes under non-preemptive scheduling, and these are the algorithms which once given the CPU, those will be once given the CPU cannot be taken away from the processes. So coming to the preemptive, it is quite contrast, wherein which preemption means priority. So preemption, the operating system moves the process from running to ready without the process requesting them. So there in the non-preemptive, everybody, you can take the case of the FCFS, there the turn comes first in and first out. So there it cannot be preempted. So they should come in line, either it may be shortest job first, or else the first come first serve, whatever the case may be, they will come in queue, they will get the things done and go back. But in the preemptive scheduling, these processes runs without the process requesting them. Like there may be a kind of time slice happening, or else there may be a kind of priority attached with the process. So whatever the case may be, or else depending upon some event, the priority changed. So depending upon the kind of preemption that it has, the priority that it has, it will get the CPU in between. So no need of waiting, or else no need of waiting in the queue, or no need of waiting for the CPU. Depending upon the priority or some events, background events, automatically the CPU is assigned to them, and the job gets done. Under this particular scheduling scheme, we can take some examples called as round robin scheduling, priority based scheduling, or else shortest remaining time next. So all these three kinds of scheduling algorithms comes under the preemptive scheduling. Let us see the logic of each and every scheduling algorithm. First serve is very simple and it comes under non-preemptive scheme, and this is a kind of queue. You can say it is a queue. Jobs are scheduled in the order that they are received. So P1, P0, P1, P2, P3, suppose if they comes in the same order, then the service will be provided in the same order, or else depending upon the arrival time also. So those particular processes will be considered in the order of arrival, or suppose at the same time most of them, like within a difference of fraction of some nanoseconds, so they had appeared, and in the same way those will be getting the services. So implementation is very easy, and then a queue of the processes will be maintained, and depending upon the queue of the processes, queue that is being maintained, the same way the CPU is allotted to them and the job is being completed. So FCFS tends to favor CPU bound processes. Once the CPU is attached to them, and all the and suppose that particular process is a CPU burst, purely a CPU burst process, then it is very like that favoring thing, wherein which the complete time is been allotted to that particular process which came in the same order, and then it is been done and thrown back to the disk. Shortest job first is nothing but the name itself is suggesting you that the shortest job will be executed first, and then the next shortest job will be taken. Likewise, among the jobs available, first of all, whichever is having the processing time very less, so that will be done first, and then later on the successive jobs will be, or successive processes will be done. This algorithm is assigned to the process that has smallest next CPU processing time, and when the CPU is available, those will be getting the chance and are being executed. In case of a time, once again the FCFS will be executed. In the same FCFS fashion, it will be executed. It is originally implemented in a batch processing environment. So shortest job first is relied on a time estimate supplied with the batch job. So along with the process, the time also needs to be mentioned, whether it requires some 20 units or 10 units or 40 units, depending upon the units of time that is going to be predicted, the shortest job will be executed first. So coming to the preemptive algorithms, the round robin preemptive algorithm is very famous and popular. This particular round robin, as you can see in the older Unix systems, Linux, and then IRX systems, the round robin says. Here the round robin scheduling algorithm is primarily used in the time sharing systems, that is for each and every time slice, or else for every quantum, obviously it should shift to the next process or else next user, you can say next user. So the quantum obviously is defined within the system software itself, like 4 units of time comprises a quantum, or else 10 units of time comprises a quantum. So that particular quantum is the main factor which will be playing the main role. So after the expiry of that particular quantum of time with one process, immediately the processor will be shifting to the next job. Even though it is having a slight job to do for the first process, but once the time expires for the P1, immediately it will be shifting to the P2. Likewise, the whole round robin will be done for the whole system, for the waiting processes, and then once again it will be coming back to the P1. It is a kind of circular queue wherein which, depending upon the time quantum or the time slice, the split will be, the shift will be happening. So basically the CPU time is divided into time slices as we had seen, and we can call this particular thing as a quantum. Each process is allotted a small time slice called quantum, no process can run for more than one quantum. So even though it just extends for some seconds, also the processor will be shifting to the other process because the time quantum has expired for the process. So this is a kind of circular kind of thing, where in which each user or else each process will get their own time slice. However, the user will be looking in a different way. He will, in the time quantum, like in the round robin fashion, each and every user will see the system as the CPU is attached to him only, because the time quantum is such a short kind of thing, where in which it will be continuously shifting from one person to the other person. Even the user cannot have an idea that at any particular time or any particular instance with whom the processor is working. That guess also can't be done. So every user will think that the processor is attached to his or her process only. So then comes the shortest time remaining next. This is a preemptive version of the shortest job first. So there is a light twist, wherein which after getting assigned some process, once again for the next process it will check which is having the least time among the arrival jobs. So every time it will see the shortest time, and the shortest time job will be assigned the next. Suppose if the same thing is happening in the shortest job, that is at one go, at the first go itself, everything is ordered. Like this is having the 20, this is having 30. Likewise, they will be lined up and the processor is assigned to them for the jobs. But in the STRN algorithm, this permits a process that enters the ready list to preempt the running process if the time for the new process is less. So every time a comparison will be done, and if the less time job is waiting in the queue, that will be serviced first, and then the other one will be waiting for the processor. So this is a kind of preemptive version of the shortest job first. So there is another kind of preemptive algorithm, that is priority scheduling or else event driven scheduling. This is the simplest kind of preemptive algorithm, wherein which in the table itself or else in the queue itself, all the process time will be mentioned, and also attached with each and every process the priority also will be mentioned. Suppose if the processes are ranging from P0 to P5 and having several processing times depending upon the process. However, for P0 the rank may be something else, and when compared to P5. So for each and every process a priority or else a number will be attached, which will execute first, even though the processing time is high, but the process is a very high priority process, so it should execute first, and then depending upon the second rank, the second process will get the chance. So here only the process number or else process time are not sufficient. Along with the process time, the priority also needs to be attached. So this is the basic difference between the preemptive and the priority based scheduling. A priority is attached or associated with each process, and the scheduler always picks up the highest priority process for execution from the ready queue. So a major problem with a priority based scheduling is indefinite blocking of a lower priority process by a high priority process. This happens obviously. Why? Because if there are several higher priority processes, the lowest priority processes will be having less attention, and also the CPU we don't know when it comes. Meanwhile, suppose if some other higher priority processes arrived, then also these will be given the less priority because they are having the less priority with them. So never ending, it will be just waiting in the wait condition rather than in the CPU execute condition. In general, completion of a process within finite time cannot be guaranteed here. Why? Because if some 5 processes are waiting attached with the priorities, and process 4 and process 5 are the less priority jobs, and while 3 priority jobs got done their job, another set of 3 processes came with the high priority. Likewise, every time if such kind of condition is applied, so P4 and P5, the lower priority jobs are just waiting to get the CPU. So there is a kind of algorithm here one can apply, that is the aging priority. The solution to this particular problem of indefinite blockage of low priority process is provided by aging priority. There is a simple technique one can like the OS can implement. What it is? Aging priority is a technique of gradually increasing the priority of the processes that wait in the system for a long time. So the OS itself should give some sort of adding on to the priority. Like suppose if 5 jobs are waiting with P1 to P0 to P4 with the 1 to 5 priority mechanism in the order. Suppose if 3 priority jobs had gone done service and left the system, once again another 3 processes came into picture which are higher priority than the P3 and P4. However, due to this aging priority, the earlier processes which are waiting will get higher priority than the just arrived processes. So eventually the older processes attain higher priority and are ensured of completion in a finite time. So with this particular algorithms, scheduling algorithms, we will conclude the session. Let us just recap what has happened, what we had studied in this session. We started with the process. And then we talked about the process states. We talked about the PCB, scheduler, types of scheduler, objectives of the scheduling, and then various process scheduling algorithms. Hope you understood this particular chapter, and in the next session let us concentrate on inter-process communication and synchronization. With this I conclude the session. Thank you.